So far what we have learned is that if we have a discrete particle system of individual particles located at discrete positions, then the center of mass is calculated as the weighted mean position of the individual position of the particles. Okay. So in other words, with respect to some XYZ system, suppose this is our coordinate frame. And in this reference frame, there are various particles like M1, M2, M3, etc. located at various position vectors. Then the position of the center of mass is defined as the symmetry point. So its position vector is given as the weighted mean, summation M into R. Divided by the total mass. So RCM is the position of the center of mass. Which is and the weightage is given in terms of the mass. So it is summation mass into R. For example, if these were charged particles and if we were giving the weightage in terms of charge, it would have been summation QR instead of summation MR in the numerator and divided by total charge in the denominator. So that is like a statistical definition, that weighted mean is where we are calculating mean position of a certain quantity, summation of that divided by the total number of terms. Weighted mean becomes some weightage factor multiplied by those terms divided by the total of that weightage factor. So here the weightage factor given is to the mass. Right. So with this, we have seen some application examples and all that. Now today, we will see that eventually we'll move on to position of center of mass of continuous mass distributions. Okay, this is for discrete particle systems. Okay, and when we come to continuous mass systems, we will see that there is application of integration. The summation is replaced with integration. But before that, let us look at some more applications of this itself, the discrete particle system center of mass definition, and how we can make use of superposition principle like we had done last time for an example problem. And also we will discuss about motion of center of mass, because that is the most important thing in terms of application. Okay. Right. So now we can also see one thing that okay, Abhinav, we'll discuss that also. Okay. So if we have a rigid body which is made of uniform density material, okay, and it's of a regular geometrical shape, then the center of mass is at the centroid of that. Okay, so for a rigid body, okay,
We've done this.
Sorry?
Done this, sir.
No, actually, I think what we discussed last time was that
Identical particles.
Like if we have equal mass particles now forming a regular geometrical shape, then the center of mass is at the centroid of that shape. So this is a bit of an extension of that. Okay, so if we have a rigid body with isotropic mass distribution. So what is meant by isotropic mass distribution is uniformly distributed mass.
Okay, sir.
So isotropic term over here means uniform with respect to space. So for example, that would be like, suppose we have a 3D object, so solid body of uniform density, that would be isotropic mass distribution. Or suppose we have a rod, but with uniform, I'm talking about a thin rod here. So thin rod with uniform mass per unit length. So this is a linear body instead of a three-dimensional solid body. But if it's a linear body, mass is distributed over length and should have uniform mass per unit length, then we will say it is isotropic. Or for example, if it is a surface, so like a thin plate, but if it is isotropic, then it has uniform mass per unit surface area. So such bodies will be called isotropic. So first of all, we should understand the meaning of this term isotropic mass distribution. So for a rigid body with isotropic mass distribution, the center of mass, and especially if that rigid body is a regular geometrical shape, so if that is the case, then the center of mass will be located at the centroid. So for example, if we have, for example, a solid sphere, which is isotropic, that means it has a uniform density, then its center of mass is at its geometrical center. If we have, for example, a solid cube, which is also isotropic of uniform density, then the center of mass is at the centroid. And for a solid cube, the centroid is the intersection point of the body diagonals. So this is our solid cube. Centroid will be that point where the body diagonals intersect. Okay, so this applies not only to solid bodies, it can apply to a hollow body also. Okay, so for example, if we have a hollow cylindrical shell with uniform mass per unit surface area, then once again its center of mass is at the centroid, which in the case of a cylinder will be the midpoint of its axis. So this kind of situation.
Sir, what's this axis?
Cylinder symmetry axis. The axis of a cylinder is the axis that you get by
Equidistant from all the surfaces.
Basically, if you cut the cylinder into discs, or in this case, hollow rings, because it's a hollow cylinder, you get the midpoint of all those rings. I mean, the centers of all those rings.
Yes, sir.
That is the axis of the cylinder. So now the midpoint of this axis. So the proper name for this axis is that it's a symmetry axis. Symmetry axis of the cylinder. So midpoint of the symmetry axis inside it, that is the center of mass now.
Yes, sir.
So if it is a regular geometrical shape whose centroid we can calculate, whose centroid we know geometrically itself, then it's easy to calculate the position of the center of mass like this. But for example, if it is not such a regular shape, like even something like a hemisphere. Now, a hemisphere is something whose centroid we don't know geometrically how to calculate, because it's not a symmetrical shape in that sense. So then we need to use integration method to find the position of center of mass.
Sir, if I was to split a sphere,
Hmm.
what happened to its center of mass?
So if you split the sphere, you're getting two individual hemispheres or whatever. One something which is larger than a hemisphere and one something which is less than a hemisphere. So individually they will have different center of masses. You understanding the point?
Yes, sir.
Okay, so now for example, how we make use of this information, calculate position of center of mass when a body is not exactly one of these regular shapes, but some kind of combination of them. So for example, we have this situation. We have a thin rod, but what we have done is we bent that thin rod into an L shape like this. So originally the rod was of length L. But now it is bent into a 90-degree angle where this section is, let's say, 1/3 the length of the original rod, and this section is 2/3 the length. So a thin uniform rod, mass M and length L, is bent into a 90-degree angle. If you want to locate center of mass with respect to the corner point O, let's say. Okay, so we've taken this corner point as O. So with respect to this point, we want to locate the center of mass. Okay, so what we'll do here is we will use superposition. That is, we will think of the L shape as a combination of two individual rods, one of mass L, one of length L by 3, the other of length 2L by 3. And those individual parts are very easy to find center of mass for, because a rod of length L by 3, its center of mass is just at its midpoint. A rod of length 2L by 3, the center of mass is at its midpoint. So we will replace each of those smaller rods, L by 3 and 2L by 3, with equivalent mass particles at their center of mass. And then we'll use the particle formula for center of mass, that is summation mr divided by summation m. So that's how we use superposition. So what we'll do here is application of the principle of superposition. That is, that the L shape is a superposition or overlap of two individual thin rods of 2L/3. Okay, so this one will have mass of 2m/3, and this one will have mass m/3. So now the concept is that each of those individual rods, their center of mass is located at their midpoint. So using that principle now, we will find the center of mass of the system. So what I'm saying is you will replace this smaller rod of 2L/3 with a particle of its equivalent mass, that is 2m/3, but that particle should be located where? At its center of mass. So that is at the midpoint of that rod. And then the L/3 rod you will replace with a particle of mass m/3, but where that particle should be located? At its midpoint. So that will be at L/6 from this corner. So
Okay,
that
sir.
leaves you with a two particle system instead of a rigid body. And for the two particle system, you can easily find the position of the center of mass. Okay, understood this?
Yes, sir.
Okay, so now what you do is you take your origin as this corner point and take x and y axis, horizontal and vertical or whatever, and locate the coordinates of the center of mass. Okay, so that's what we mean by locate the center of mass with respect to the corner point. Oh. So that's how we are making use of the principle of superposition here.
So is my answer correct?
Just checking. Yes, anyway, that's correct. Okay, so you have found the distance, no, Janvi, of that
Yes, sir.
point. Okay, right. So let's verify this answer now. Just a moment. Right. So let's verify this. So the first thing we'll do is we will replace this L-shaped rod So now if we are taking our coordinate frame such that this is our x-axis and this is our y-axis, then we will think of this section as it has mass m1, which is m by 3, and its center of mass is located at this midpoint. And we'll think of this section as if it's a particle of mass m2, which is 2m by 3, and its center of mass is here. So now we have replaced our original system with an equivalent two particle system, where the two particles are now located at this position here and this position here. Now this should be basically the midpoint of this rod. So its coordinates are 0, L by 3. And this is the midpoint of this rod. So it's at L by 6 from the center. So its coordinates are L by 6, 0. So now the system center of mass will be somewhere here. So that is the final center of mass of the rod also. So its coordinates are, let's say, want to find out. So that becomes the position of the center of mass.
Sir, I did with the method of the mass movement is about the center of mass is 0.
You have to use the definition of the center of mass position.
So with that method, our answer is coming different.
Yes, that's what I'm saying. No? That's why I use the definition of center of mass. The definition of center of mass is this. XCM is summation mx divided by summation m.
Sir, in that method, in this question, can we use that method about this?
There is no other method, beta. You have to use this definition of center of mass. There is no other method of finding center of mass. Moment is a different thing, beta. Moment we'll discuss when we come to the chapter of rotation and we understand moment of force, moment of linear momentum, all these things. Okay. This is the definition of center of mass, and this is the method you have to use here. There is no other method of finding center of mass.
Okay, sir.
You can also see that if you want to calculate this distance OC, that is root 17 by 4. Okay, so hope this is clear to all of you. Okay, now next example, see a bit of an extension of this concept. Okay, so in this example, what we have is to begin with a solid, a thin disk like this. But from that thin disk, what we are doing is we are cutting a hole into it, a round hole. So this is a thin disk of radius r with a round hole. That hole has diameter equal to r, and the center point of the hole is minus r by 2 comma 0. So this is the center of this hole, and this diameter of the hole is r. So the original disk would have had its center of mass at the origin if we had not cut out the hole. Okay, but now we have to find the position of the center of mass. Of this body. So this says uniform mass distribution. That is, its mass per unit surface area is uniform. It's isotropic. Now, logically, you can see which side the center of mass will be. Obviously, it will not be at the origin, okay, because we have cut out a hole. So where will it be? Will it be somewhere in the first quadrant? Will it be on the y-axis?
Along positive x-axis.
Yes, it will be somewhere on the positive x-axis. Very good, because that is still an axis of symmetry, no? You can see. And there is more mass on the positive x side than on the negative x side. So the center of mass has to shift to somewhere having a positive x coordinate but a 0 y coordinate. So now how we can use principle of superposition here to find the center of mass? Can you tell me?
So we can find out the area of the subtracted object and
Yeah, so fine. Like if the original disk had mass m, now you can say that the disk that you've cut out, the small disk of radius r by 2, that has suppose mass m1. You can find that out. And the remaining mass that we have over here, that is m2, you can find that out. But for center of mass, how we'll use superposition now? So what we know is that if we place back the mass that we had cut out, okay, if we place back that smaller disk, then the new system that we'll get, which is the sum of those two things, the smaller disk and the remaining part, which I've shaded over here, their center of mass is going to be where? At the origin.
Yes, sir.
Okay. So it's like you have a small disk of mass m1 whose center of mass is where? At minus r by 2 comma 0. and you have the remaining mass, the shaded mass over here, which is M2, whose center of mass I don't know. It is at some x coordinate comma 0. But the combination of those two things, M1 plus M2, their center of mass should be where? At the origin. So we can make use of that information to find the position of the center of mass of M2.
So now is my answer correct?
Okay, so let's verify the answer. I've received a couple of them, but unfortunately, yes, Anirudh, your answer is correct. Good. I mean, that is not unfortunate. Couple of answers I've received are not correct. That's unfortunate. Anyhow, doesn't matter. So let's see how we will find the center of mass. So let's say the original disk that I had before cutting out the hole in it. This original disk, suppose. This disk was of mass m and radius r. Okay. So now if I cut a round hole from it, this disk is of mass m1, let's say, because its radius is r by 2. Therefore, this mass m1 will be m by 4. Okay. If it is of same material as this. So now what will happen is if I cut this round hole out from the original disk, then the remaining part that I have, that is of mass how much? 3m by 4. So this mass m2 m by 4 beta, because see, this has something called surface mass density or mass per unit surface area, say sigma. So this one's mass m1 will be that same sigma into its area.
Okay, sir.
So you can think of it like this also. That's why this will become 3m by 4. So mass is in proportion to surface area. So now what is happening that this mass is a superposition of these two. So in other words, if I have a situation where this mass m1 is placed here and this mass m2 is placed here, then this combination of these two objects, their center of mass should be where? It should be at the origin of my system. So if the m2 mass has its center of mass somewhere here, which is at some x2 comma 0, But the M1 mass has its center of mass, we know over here. This is at minus r by 2 comma 0. Then the system center of mass should be where? At the origin. So M1 plus M2 as a system is equal to M. So it has center of mass at 0 comma 0. Give back to that kind of situation, that replace that whole thing, the disk with the hole, with the equivalent mass M2, which is 3m by 4, but at some x comma 0 value we don't know. Whereas replace the mass M1, which is m by 4, at a position that we know, it's minus r by 2 comma 0. Now this system center of mass should be located where? It should be located at the origin. So M1 x1 plus M2 x2 should be 0. That is the meaning of application of superposition. Superimpose the actual mass that you have, which is M2, with the mass that you had cut out from the original disk, which was M1. So you're getting a symmetrical shape, which is the full disk. So M1 over here is m by 4, and its center of mass position is minus r by 2. M2 is 3m by 4, but its center of mass position is unknown. But their combination is having the center of mass at the origin. So I can take m by 4 common here. I have minus r by 2 plus 3x is equal to 0. So x is r by 6. The center of mass of M2, which is the disk with the hole, that one is at r by 6 comma 0. So the superposition of the portion cut out with the portion remaining is equal to the uncut disk.
So done.
Two minutes, sir. 2 minutes. I'm just waiting.
Alright. Okay, done.
So yes, sir.
Yeah. Okay, now from here we will move on to motion of center of mass. So if we have a discrete particle system and one or more of the particles are in motion, then most often the center of mass is also in motion. Though it can also happen that the center of mass is at rest while the individual particles are in motion. That's also possible. But generally speaking, if the center of mass is in motion, then how do we calculate the kinematics parameters like displacement, velocity, acceleration, etc. of the center of mass? So in terms of working principle, that's very easy because we already have a formula for position. We just need to apply the kinematics definition. Okay. So position of center of mass at any instant is given by summation of mr divided by summation of m. So if the individual particles if at least one of the particles that means so displacement of center of mass be defined as the kinematics parameter change in position. It is a vector difference of final position minus initial position. So this is our kinematics definition. So applying that definition to this situation now, we can see that the displacement S of the center of mass becomes delta or change in the weighted mean of the individual positions. Okay. So summation mr divided by summation m. Now at the moment we are talking about a discrete particle system where the individual particles are of fixed mass. This is for a discrete particle system such that individual particles have fixed mass. They're not having variable mass. Variable mass system is slightly different treatment. We'll come to that later. So here we are talking about constant mass or fixed mass systems. So that means mi are constant. Okay. So when we apply this summation inside this bracket, the denominator is totally independent of it, and the summation in the numerator goes and applies to the positions because they are variable, but the masses are fixed. So that way we'll now see that this becomes summation m into s because change in position of any particle is the displacement of that particle. So we have a very symmetrical definition for displacement of center of mass, like we have for position. Just as position was the weighted mean of the individual positions, like that the displacement of the center of mass is the weighted mean of the displacement of the individual particles. So that is why we can have a situation where the individual particles are moving. So therefore they have displacement, but displacement of center of mass is zero also, because there's a vector sum after all. Okay.
Okay, sir.
But in general, we can say that if the particles within a system are moving, the center of mass may be in motion, the center of mass may be at rest. So if it is in motion, then the displacement is given by this.
Sir, for a person moving on the circumference of a circle with uniform velocity, how does the relative motion of the center look?
Tanvi, what was the question?
So the question is, for a person moving on the circumference of a circle with uniform velocity, how does the relative motion of the center look?
For a person moving in on a circle with uniform speed, na?
Yes, sir.
How does the motion of the center of this thing look? Na? So that
Yes, sir.
will be a circular motion.
So for a person on the circumference, the center will look to be in circular motion.
Yes, because the center always looks like it's equidistant, but the orientation of the center is changing. Na? You understand? Na?
No,
So
sir.
there's many ways of proving this also, but see what is happening is that if a person is in circular motion, then their instantaneous position at any point of time is like this, na? That the position of that point with respect to our origin is what it is, r cos theta. Now if it's going with constant angular speed, because it's going with constant speed, we can write this as this. So now what is the, so the velocity of that person, for example, at any instant is r omega minus sine omega t I cap plus cos omega t j cap. Okay. Now from this you can see that the velocity of the origin with respect to that person will become minus of, this, no?
Yes, sir.
So this is 0. Okay. So it is minus of Vp. So it is just like a circular motion with the reverse angular speed, angular velocity.
Okay, sir.
Now the thing is, while you are running around the circle, if your eyes are fixed at the center, then you will not perceive the center to be going in circular motion. But that is like, saying that if you're standing at the center and you're observing a person running, and if you keep turning as that person is running, that person will appear to be at rest to you, no?
Oh, sir. Yes, sir.
Understand the point, no? Okay.
Then, sir, for what? So, what is this orientation? Then, for what orientation will it seem like the center is in circular motion?
That is if you keep your eyes in a fixed direction. Like let's say this y-axis is pointing north, so your eye is always pointing north. So you're seeing the origin move around in peripheral vision. No?
Okay, sir. Okay.
Okay, so then you understand, it will appear like the origin has gone round you in one complete circle. Because when you started from the x-axis, the origin was to your west. You know? Then by the time you reach the north, the origin is to your south. Then by the time you reach the negative x-axis, it's come to your east, like that. No?
Yes, sir. I got it.
Okay, so let's understand this displacement thing with an example. So suppose we have this situation. That we have at t equal to 0, we have a particle of mass 2m over here, and we have a particle of mass m over here, these two particles. Now, after some time, B has moved here, and E has moved here. So B has moved by a displacement of, let's say, 4 I cap, and A has moved by a displacement of 6j cap in meters. And let's say the original position of this one was this, and this one was. So find the displacement of the center of mass. Zero to t time. Okay, so in such a question, I mean, one would think that, okay, logically, let's find the original position of the center of mass, let's find the new position of the center of mass, and then calculate the displacement as the difference in position. But we don't need to do that. What we need to do here is directly apply the definition of the displacement of center of mass, that it is the weighted mean of the individual displacements of the particles. Yes, very good, Anirudh. That's correct. So what if we use the direct formula method? You can see that displacement of the center of mass, I'll write as this kind of weighted mean. Now we can also verify like this, that originally where was the center of mass located? It was located at somewhere here, right? So this distance is 3. So the center of mass would have been located here at 1, 0. Okay. And now where will the center of mass be located? Be located somewhere here, where the new x coordinate would have become 6 into 2 minus 1 divided by 3, 11 by 3. The y coordinate would have been 0 plus 6 divided by 3, so 2. See that this is the displacement vector of the center of mass, which will agree with this. 11 by 3 minus 1 is 8 by 3.
So done.
And now, okay. Now logically, the next thing we'll see, once you have seen how to calculate the the displacement of center of mass. So logically, the next thing for us is that if the particles are in motion with some instantaneous velocity, then the center of mass might also have some instantaneous velocity. So how we calculate the instantaneous velocity of the center of mass? Okay. But just before that, we'll also understand that it can always happen that individual particles of a system have moved, but the center of mass has not moved. Okay, so we can, for example, have a situation like this, that we have three particles like this, which are of mass 2m, m, and m, respectively. Okay. And suppose now what is happening is that, so these are E, B, and C, and the center of mass will be somewhere here. So this is in a XY system like this. It can happen that after some time, A and B have moved like this, and C has moved something like this, but the center of mass has remained here. So if displacement of A is, let's say, minus 5 I cap, and displacement of B, let us say, plus 2 j cap, find the displacement of C such that the system's center of mass should remain at rest. So that has zero displacement. So it's very easy here. What you'll have to do is displacement of center of mass is zero, means that summation of mass into displacement should be zero. That's all you have to apply over here. So that is why you can see the direction of the displacement of the third particle C I have predicted is like this. So that, as you know, vectors, they can cancel. The summation of m into s are individual vectors. So there, the product of m into s is a vector. So summation ms is a vector quantity. It can become zero. In this case, if the direction will be something like this. We have a positive x component and a negative y component. So all we have to do here is apply that. So for A, it is minus 5m I cap. For B, it is positive of 2m into 2. So plus 4m j cap. And for C, it is m into SC. But this should be 0. That's in meters because so this will now, this condition will satisfy the fact that the displacement of the center of mass is 0. So originally our system was three particles at the corners of a triangle like this, so that the center of mass is somewhere here. So after some time, it's like this is moved by 5. gone somewhere here. Comparison, this has moved only 2. So let's make this a little bit smaller. So this will have to move somewhere here so that the new triangle that we get still has the center of mass at the same location. Still has the center of mass. Okay, so this shows us that particular situation where even though the individual particles of a system are moving, the center of mass does not have any net motion. Now, in that regard, let us continue to the next definition: velocity of the center of mass.
So could you please hold up? I was actually noting it up.
Yes.
Yes, sir. Done.
Okay. So about definition for velocity of center of mass is that same logical definition. Instantaneous velocity of any point, kinematics wise, is defined as rate of change of position or instantaneous rate of displacement with respect to time. So either way we can define it in terms of instantaneous displacement or instantaneous position, because in a small time dt, the displacement ds is the same thing as the change in position dr. Okay. So whether we define it this way or this way, it's one and the same thing. So that means that write it as rate of change of summation mr, for example, divided by summation m. So again, keeping in mind that all the mi's are fixed. Okay, so this becomes summation of m into rate of change of position, or you can also write that as rate of displacement in the numerator, divided by summation of m in the denominator. So velocity of center of mass also becomes weighted mean of the individual velocities. So it's only logical that it follows the same type of definition, that it is a weighted mean. So once again, it is possible that individual parts are moving, but the center of mass is stationary, because the vector sum of m into v is 0. Okay, that's always possible. Okay, now the thing is, this definition here of velocity of center of mass has a larger implication actually in terms of the next thing we'll define, which is linear momentum of a system. We have seen that an individual particle's linear momentum is defined as mass into instantaneous velocity. But what about a system? How do we define the linear momentum of a system? So we define it like this, that linear momentum of a system of particles is equal to the total mass multiplied by the instantaneous velocity of center of mass. This is the definition, where capital M is the total mass. So in case of a discrete particle system, it is summation Mi. Now from the above definition, we can also see that VCM is summation MV divided by summation M. So it can be written as vector sum of the momenta of the particles divided by total mass. So for a system of particles, of discrete particle system rather, the momentum of the system, which is total mass into velocity of center of mass, can also be described as the sum of the vector sum of the individual momenta of the particles. Again, for a discrete particle system. So this becomes a very important understanding. Okay. First of all, the definition of linear momentum of a system of particles, whatever type of system it is. Yes, Janvi.
So this formula gives us the average velocity, no?
No, but average velocity is a different thing. Momentum is a different thing. Momentum is an instantaneous
Above this.
quantity. Huh?
The above, one above this.
No, that is weighted mean beta. BCM is the instantaneous velocity of the center of mass. The average velocity, when you talk about that, it is the time average. So that is total displacement by total time. But this is instantaneous. You understanding now?
Okay, sir. Yes.
So yeah, in words, you can always write it like this, that the VCM is the weighted mean of the velocities of the individual particles. The center of mass velocity is the weighted mean. When we say average, it generally means time average. Right? But here it is weighted mean, where the weightage is given to mass. Yes, Anil.
So if we put the center of mass, velocity of center of mass formula in the center of mass of the, the momentum system formula, then the mass, total mass of the system will get cancelled.
How it will get cancelled with that?
So because velocity of center of mass formula has a denominator.
But the numerator is summation MV, no? You understand? No? Rather, what we are doing is we are cross multiplying this. No? If we take the denominator to this side, it becomes total mass into velocity of center of mass. That is summation Pi, no? Because M into V for individual particles. Understood, no?
Yes, sir.
So it is like, we are cross multiplying. The denominator is taken to that side. So we're getting total mass into velocity of center of mass. That is equal to summation MV. Now that total mass into velocity of center of mass itself is defined as what? Instantaneous momentum of the system.
Yes, sir.
So at any point of time, now we have this final definition below, that at any instant, the instantaneous momentum of the center of mass is basically what? The vector sum of the momenta of its particles.
Yes, sir.
So for example, very soon in thermodynamics, you will come to something called kinetic theory of gases, which will explain to you that in an ideal gas, at somewhere around room temperature, or in that range of temperature, the gas molecules are moving about very fast. They have an average speed which is called the RMS speed, which is kind of comparable to the speed of sound. So it's a pretty large speed. But if we calculate the velocity of the center of mass of the system, or the momentum of the system, it will come out to be zero, because the vector sum of the momenta, because they are moving about in random motions with continuous collisions happening. So the directions of velocities of the individual gas molecules are distributed over three-dimensional space in a random manner. Now, because you have like literally billions and billions of gas molecules in a container, now Avogadro's number is such a large number. So when you have random motion over such a large sample space, the summation will always come out to be zero, because whatever number of particles are moving in a particular direction at a given instant, you will always find almost the same amount of particles moving in the opposite direction. So their momenta cancel.
Yes, sir.
So even though the gas molecules are moving about very, very fast individually, but if you look at the total momentum of the gas molecules as a system inside a box, that momentum is zero. They have individual momenta, but the system's momentum is zero. Okay, now this definition of momentum further has a very important significance, because from the definition of momentum, we will come to dynamics of a system of particles. That is, what causes change in momentum, the force versus momentum relation, Newton's second law, which is now going to be called impulse momentum theorem for us. So let's come to that. So further, so linear momentum we've got. So now if we differentiate this equation, rate of change of linear momentum of the system, that will become, from the last definition that I've written, it is rate of change of summation of pi for the n particles. So that means rate of change of momentum of the system is equal to summation of rate of change of all the particles. Now by Newton's second law, applied in a particle sense, so particle dynamics, the rate of change of any particle's momentum is equal to the net force acting on it. So this becomes summation of the net force acting on all the particles summed up over all the particles. So ultimately this summation is basically what? It is a vector sum of all the forces acting on all the particles put together. Because Fi is the vector sum of all the forces acting on a particular particle. And then we are summing that up over all the particles. So ultimately we are summing up all the forces acting within a system. So this net force, it is the vector sum of all forces acting on that particular particle. Acting on that ith particle. So therefore, summation Fi will become the sum of all forces acting on all particles of the system. So when we do that summation, what happens is that now when you notice on any particular particle, there is two types of forces that can act, internal and external. So internal are those forces which are acting within the system. That means one particle is applying some force on the other. So the other is applying some equal and opposite force on the first. So those internal forces will always be present in action-reaction pairs, and they will cancel off. Whereas if a particle is experiencing some external force because of some external agent external to the system, okay, not internal within the system, then the reaction for that force is the reaction that that particle is applying on the external agent. So that is not present within the summation. So that doesn't get excluded. Okay, so next we'll understand when we do the summation of these forces, the summation of Fi, because we are adding up all the forces, just understood. This will, what will come up with is now the net external force. That is the sum of all the external forces acting on the system. Okay. Because internal forces cancel in action-reaction pairs. Newton's third law. So the right hand side of this equation, the rate of change of momentum equals to that summation of all the forces. Now we'll be left with only the net external force. So the statement now becomes that the net external force acting on a system is equal to its rate of change of momentum. So that is rate of change of total mass into velocity of center of mass. So this momentum of the system, therefore, is not affected by internal forces. It is only affected by external force. If you look at an individual particle within the system, that individual momentum can be affected by the internal force acting on it. But the total system's momentum will never be affected by any internal force. It will only be affected by external forces. So this is a very, very important concept. And from this, we will look at the situations where we can apply conservation of momentum if the net external force is zero. So it's very important you understand this whole chain of logic. Okay? Starting from the definition of momentum of the system to applying rate of change on that concept, and within that summation of forces, applying the concept of Newton's third law, that internal forces present in action-reaction pairs will cancel. So when we look at applications of this, I'll explain to you with examples also, which are internal forces, which are external forces. Okay.
So noted. So noted.
Okay. Okay, so let's now understand this. So first of all, this equation now represents Newton's second law for a system of particles, or dynamics of a system of particles. Okay, so that's the difference. So, for example, if we have a situation like this now, let's understand this business of internal and external forces first through an example, then we will come back to the next thing in theory. Now, here, suppose this is a smooth surface. And these two are connected by a spring of constant K, ideal spring. Now I'm applying some external force like this. And what I'm observing is, as a result of that, this is moving with acceleration A1. This is moving with acceleration A2. But it is given to me that so now suppose at some instant, if the force applied is, let's say, 6 newtons, okay, and A1 at a particular instant is, let us say, 1.5 meters per second square. Find acceleration of the center of mass and find acceleration of block 2 at this instant. So one way we can solve the system is, for the first part, apply dynamics of system of particles. And for that, take the system as the sum of the two blocks plus the spring. Okay. So spring is massless actually. So the total mass of the system will be M1 plus M2. Okay. So when we apply dynamics, we'll say that the net external force is equal to total mass. First step is rate of change of momentum. So that will become so when we apply this, that the net external force acting on the system is total mass into acceleration of center of mass. When we apply this over here, we'll be left with F is equal to M1 plus M2 into ACM. So we don't need to make any free body diagram and all that, because the net external force acting will be only F. That will only be F, because when we look at the free body diagrams, we'll understand that at any point of time, if the spring is having a compressed length, let's say, so the spring is applying tension like this and like this, but this is within the system. What is acting from outside the system is this external force F, the weights, and the normal reactions. So these are the external forces. So the net external force is only F, because N1 balances M1G and N2 balances M2G. Whereas the tension in the spring, which is Kx, that is internal. So we don't need to include that in our system dynamics. So the answer to the acceleration part is actually very simple. We don't need to solve the FPD and all that. We just need to substitute the values, that we are applying an external force of 6 newtons and total mass of the system is 3 kg. Then the acceleration of the center of mass will be 2 meters per second square. That's done with the first part. Now this, for the second part, that is where your free body diagrams will come in. So just try that out also. Okay.
So can't we just equate M1A1 plus M2A2 by M1?
Yes, that's another thing that we can do. That later when we see the definition of acceleration of center of mass, just like the definition of velocity and displacement, center of mass's acceleration will also be a weighted mean. But it will be the weighted mean of acceleration. So it will be M1A1 plus M2A2 divided by M1 plus M2. So now we know ACM and we know A1. It's given to us in the question. So at that instant, the value of A2 we can find out by just using that weighted mean definition. So we can avoid particle dynamics and FBDs and all that altogether. So that's also correct. You can use that method also. Okay. So tell me, how much will be the acceleration A2 at the moment when A1 is 1.5? Just try to work it
3
out.
meters per second square.
Sorry, how
Yes,
much? 3?
Yes,
Yes,
sir.
sir.
Okay, correct. Okay, because 2 into 1.5 plus 3 into 1 divided by total mass 3 should give you 2. Yes, that's correct.
Sir, how would we solve the second part using the FBD method?
I'll explain just a moment. So FVD में देखो क्या होगा? What is the unknown quantity Kx ना? The tension in the spring.
Yes.
So M1's FBD, in that what is happening? You know the acceleration, you know the external force, but you don't know the tension. So you calculate it from there. Okay. And now come to M2's FBD. तो उसमें net force कितना add कर रहा है? Tension.
Yes, sir.
So when you apply the individual particle dynamics to M1, then you have to consider all the forces acting on M1, not external, internal, because you're just considering one particle. So M1 पे net force कितना होगा? It will be F minus tension. Whereas M2 पे net force कितना होगा? Tension. So another thing you will see that if you write the individual equations for M1 and M2 now, the sum of those two equations will always give you the equation for the system. So this F that we have got now, that is M1 plus M2 into ACM. If you relate that equation with the individual equations, that net force on M1 is how much? F minus T, and that is M1A1. And net force on M2 is how much? That is T, and that is M2A2. So if you relate these two equations, you'll also get the equation for the acceleration of center of mass.
Yes, sir.
Okay, so let's say if I was to, if I'm not going by the weighted mean definition of acceleration of center of mass, okay, if I just want to go with dynamics right now, so how I will calculate the acceleration of the second block at this instant? So I look at the individual FBDs. I'll see that on the first block, F is acting and spring force Kx is acting, and it has some acceleration A1. On the second block, only spring force is acting. Vertical forces I'm not showing because they are balancing out anyway. So I have F minus Kx is equal to M1 A1, and I have Kx is equal to M2 A2. So here F is given to me, it was 6 Newton, Kx was unknown, okay, and this acceleration was given to me. So from this I know that Kx is how much? 6 minus 3 or 3 Newtons. So I'll substitute that here. So I'll see that 3 is equal to 1 into A2. So I'll get A2 is equal to 3 meters per second square. But alternately also see that if you add the two equations 1 plus 2, you get F is equal to M1 A1 plus M2 A2. So you can see that F divided by total mass, which is basically acceleration of center of mass, is M1 A1 plus M2 A2 divided by total mass. So actually they are consistent equations, because later we will see this is how we will define the acceleration of center of mass also. Acceleration of center of mass will come from the rate of change of velocity, instantaneous velocity. So the same process, you are calculating rate of change of summation mv divided by summation n. So it will ultimately become summation of m into acceleration divided by summation of n. So vector definition. In our particular case here, I just made it a 1D equation. So acceleration of center of mass likewise is also weighted mean. But also the net external force acting on this kind of a system, because the mass of the system is constant, total mass is fixed. So that is also equal to total mass into acceleration of center of mass. So for solving this question, I could have used either of these definitions. This one to find out A2, or I could have found out from individual FBDs like I've done above. So hope this gives you a good starting point to understand about dynamics of system of particles. Okay. Now we have a lecture tomorrow, so that's good because we have to discuss things in continuation. We have less than 24 hours now for your next lecture, 22 to be precise. But just one more thing before we wind up. We have this equation that net external force on a system is equal to rate of change of its momentum. This implies that if the net external force is 0, and such type of a system we call as a mechanically isolated system, then it implies that its momentum is conserved. So net external force, it doesn't mean that no external forces are active. It just means that the net external force is 0. Like for example, in the above question, if there was no external force acting horizontally, and you had just compressed the spring and released the blocks from rest and all that, if you had a system like this with no horizontal force acting and it's on a smooth surface, then this would be a system where the net external force is 0. So even though at some instant the spring might be applying force on these two like this, but because there is no external force, so this is a system where the net external force is 0. If I'm not applying, so if the net external force is 0, then the system's momentum is conserved. It's constant in momentum. So this is an important category of applications which we'll see, which is momentum conservation. Your class on Wednesday, is it? Oh, okay. Then we have more than 24 hours. But somehow I saw in the timetable that we have. Oh, right. It's Wednesday. Right. Good. So you have some time. Okay. So yeah, I will be sending you a revision worksheet for this thing. What we call it? The
Circle motion.
for circular motion. Yes. Okay. So that is assuming you have completed the module, or at least most of the questions of the module. And I also have physical doubt sessions at almost I think all the places this week. Kharghar I'm coming to, Nerul I'm coming to, and also Kopar Khenna, and of course Thane. So please, anything pending in circular motion, whether it's a conceptual doubt or especially that part, instantaneous radius of curvature, then vertical circular motion with application of work, energy, and all that. Okay. Please make sure all that is completed. Try to complete it before Wednesday's lecture only, because Wednesday onwards things will become quite hectic with this chapter. We are coming to the main crucial part of the chapter, and the most important in terms of applications, and one of them is conservation of linear momentum. So we are coming to that section. Okay. So, and of course we will also be coming to the integration applications for calculation of center of mass. So that's going to be very important, because we will see a different type of integration in that. Till now, you've seen integrations in kinematics type situations where you are doing integration of time varying quantities with respect to time. But now we will see what is called geometrical integrations, like, integration over position or space. So that's a whole important section. Okay. Anyhow, so that's it for today's session. People, wish you all the best and have a nice day.
Thank you, sir. Bye, sir.
Thank you,
So what
sir.
about homework?
Yeah, so I will send you some specific questions to do from HC Verma from center of mass. And also, as I said, I'll send a revision worksheet from circular motion.
Okay, sir.
Okay.
Thank you, sir.
Sir, if possible, can you send the homework before 12 o'clock?
Okay, I will send it before.
Thank you, sir.